And thank you to all the organizers for the invitation. I'm glad to be here to talk to you about this topic. And we're going to sort of take a larger view now. We're going to zoom out and talk about the sources and also the exposure and health effects, or at least how to assess these things. So, I'd like to start with Lance Wallace's 1996 paper, Indoor Particles, a Review. This was really a landmark paper, and at that time, summarizing existing studies in this fairly new field, he found that the major sources of indoor PM were smoking, cooking, and unexplained. The personal cloud, which is that the exposure, if you take samples in the breathing zone of a person, is higher than what is predicted from the indoor monitoring. This was observed but not yet investigated. And also personal PM exposures are not well correlated with outdoor PM, although if you looked at individuals over a long time, you could see the correlations. So what have we learned in the last 25 years? This is a long time. And actually, for me, this is I started my PhD right after this paper came out and focused on the personal cloud. We still see that smoking and cooking are major indoor sources, and now we have these unexplained sources, many of them figured out, although as you've already heard today, the details of these things, like the contributions from various sources and the chemistry indoors, we still have a lot of work to do. So some large questions. So how does the indoor environment impact the concentration and the composition of the indoor PM? So we have all these sources. We also know that the occupants themselves affect the composition and the concentration of the indoor PM, the building operation, potentially any kind of filtration or other devices, and also pollutant or microbial cycling, that is thinking about the deposition and resuspension cycle, and also chemistry, and so on. So also what we've talked about today is how does the indoor PM impact human health? And we have both acute and chronic effects, and how do we assess these health risks? We already discussed structural, well, we haven't discussed the structural influences, but we have talked about the disparate PM 2.5 exposures. But as Sunny mentioned, this is systemic, and so there are structural influences that we can determine causing these, and also figuring out mitigations. So the workshops in the next couple of weeks that really address numbers 2 through 4 here, and I'll just touch on them today. So already we discussed outdoor sources of indoor PM, outdoor transport and chemical transformation. So outdoor to indoor transport and chemical transformation. There's also indoor to outdoor, but that's not as relevant to our talk today. And then indoor sources of PM 2.5, cooking, secondary organic aerosol, third-hand smoke, the indoor microbiome, also partitioning of SVOCs and organic gases. But there are other major indoor sources that I've already mentioned: smoking, also candles and incense, heating, especially solid fuel heating, which we still use in the United States in many regions. Also shedding and resuspension, very much associated with the activities of people indoors. And the shedding and resuspension, if you look at the composition of those, there's both chemical and biological components. So indoor PM, the sources, we often see these episodal events, right? So we have short-term high concentration pulses. And so this is true for cooking, for smoking, human activity. So if you walk across the room or sit on a couch, you get a peak of concentration. Secondary organic aerosol event, you would get a peak. And you can see that there is a peak, but then also this decay. So the concentration stays elevated, but it decays, with the deposition and the exfiltration of that. This plot here, let me go back, is very typical of a concentration time series where you see PM on the y-axis and the time on the x-axis. And this is for a school in Portugal. And you can see that the concentration bumps up at the beginning of class when people arrive, when the students arrive and get settled, and it kind of goes down even though they're present because they're not as active. And you can see these peaks associated with this high activity and then the decrease, the decay again with deposition and air exchange. And so this is very typical of a concentration time series for indoor. And again, you can see these peaks. There are indoor sources, however, that are more continuous, like a stove pilot, a heating source. So there are definitely indoor sources that are more constant, but we often see these high peaks. And if you look at trends over time for indoor versus outdoor PM 2.5, you can see that these are data from 25 homes over several months in the heating season in Rochester, New York. So indoors and outdoors, the red is indoor and the blue is outdoor. And so this is the average data. I should say combined data. And you can see that there is a very regular, let's go down here in the bottom left. We can see a very regular pattern for indoor air and one for outdoor air where the concentration for the outdoor air is low and then increases during the day, mostly due to traffic. The indoor concentration, you see it bumps up as people get up and then they might be at work or they might be at home. Again, this is the data is compiled. And we see a bump here at around dinner time from cooking and also resuspension activity and potentially heating with wood appliances. So very regular. And the other interesting thing is we see such a difference on weekend versus weekday. So you can see the outdoor concentration is higher during the week, and then the indoor is more during weekend because people are home. So this is in a place where, this is Rochester, New York, and the outdoor concentration of PM 2.5 is relatively low. I'm just showing normalized levels here, but the average is close to about 10 micrograms per cubic meter outdoors. So with these indoor peaks, high concentration peaks, how does that affect health effects? Well, we know that the short-term increases in PM 2.5 outdoors anyway are associated with increased mortality. And so there's also evidence that short-term exposure to PM 2.5 affects morbidity. And we know that specific constituents of that PM 2.5 also are associated with health impacts. But we do need more data and more results for the association of short-term effects with morbidity, and as well as indoor PM 2.5 versus the outdoor. So this is really important to get the better exposure estimates of indoor PM 2.5 to assess acute health effects such as myocardial infarction that we know are associated with peaks of PM 2.5 concentrations. We also know that indoor particles may be more toxic than outdoor particles. There are several studies that indicate this, inflammatory responses and allergic reactions. This study is for PM10, but also Long et al. Found a pro-inflammatory response for rat alveolar macrophages that higher for indoor versus outdoor. So we know that there are potentially higher toxicity for indoor versus outdoor particles. So it's another reason to pay attention. So what about the chemical composition overall of indoor PM? Well, we know that we have outdoor and indoor sources that impact indoor PM. So we talked about the outdoor sources this morning and some of the indoor sources today. And as Dr. Marr discussed, you know, we'd like to approach this sort of mechanistically. What are the emission rates for these different sources? And so we can figure that out, right? What are the emission rates for these different sources? But then the aerosol is processed when it's in the air. And we've already talked about that quite a bit today as well. So it's enriched by occupant organics, squalene, cholesterol, fatty acids. It's also, the aerosol would be enriched with chemical additives, plasticizers, flame retardants, surfactants. And this is a slide stolen from Charlie Weschler from the 2016 indoor air presentation, where you can see that the SVOCs and the inorganic gases are partitioning between the gas phase and the particle phase in the air. And there are effects with temperature and relative humidity, also outdoor to indoor transport and chemical transformation. So there's quite a bit going on and a lot of complexity. Lindsay talked a little bit about the indoor microbiome and the effect of relative humidity. Here, this is a slide from 2015, Preston and Meyer, where they just summarize the different sources of bioaerosols, so microbial bioaerosols indoors, including humans, pets, plants, plumbing systems, heating, ventilation, air conditioning, mold, and resuspension of settled dust in outdoor air. So many sources of these microbes. And we know quite a bit more about viruses this year with the SARS-CoV-2 and how they're emitted and transported through a room. The 2017 report from the National Academies summarizes the research at that point on the indoor microbiome and the connections between the microbial, the human, and the occupants in the built environment. And so, so there's quite a bit known in that area. As far as source apportionment, now with we can use, the source apportionment techniques like positive matrix factorization to determine the sources for human exposure. And a lot of this work has been done for outdoor air, but more recently, we're seeing work for indoor air, and Dr. Waring has done some of this work as well with Pete DiCarlo. This shows the Shang et al. Study from 2019, source apportionment for 2 cohorts in Beijing. And you can see that for the source apportionment, we've got roadway dust and soil dust, industry and combustion, secondary or inorganic source. This cadmium source is associated with smoking. And so you can see the types of sources that are important there. And this is where we have relatively high outdoor, well, very high outdoor PM 2.5. So much of this is outdoor sources getting inside, but there's also indoor sources like household heating and smoking. So Brent brought up this study, a recent study by B et al., but this shows you the difference between the outdoor and the outdoor source that's infiltrated indoors and the indoor sources. And this, what makes the study really interesting is that they did not deploy the monitors. They used purple air monitors that were already on the purple air database, so that they could pull the data and apply it to determine, okay, if we look at indoor and outdoor monitors, so outdoor monitors nearby indoor monitors, when you put one of these monitors in, you say whether it's indoors or outdoors. And they use that to determine the infiltration factor, which at 0.26 is on the low end of the ranges that were presented by Brent. It really can be very powerful, though, that we could use these low-cost sensors to figure out, okay, what's coming from outdoors and what's coming from indoors. This is an optical-based sensor, so any kind of ultrafine particle source wouldn't show up as well, but it still can be quite useful to separate these sources. And another important finding was that they found that below about 30 micrograms per cubic meter, the indoor sources contributed more substantially to the personal exposures, and you can see that here, where the red is the indoor generated source and the blue is the outdoor infiltrated. The mass balance model is used very regularly for assessing indoor concentrations and human exposure in the indoor environment for indoor PM 2.5. And so I'm not going to go over the model now. It was already been presented today, but it can be quite powerful and very useful for most sources. So if we know, this is a lot to figure out, especially when you have phase change and coagulation and chemical reaction, inactivation for viruses, for example. But it gives us a framework to estimate these parameters and determine what the concentration and exposures could be. But it's not always, doesn't always work, so it depends on the source. And this is a study by Brandon Bohr's group where you can see the robotic baby crawling, and the concentration in the zone, in the breathing zone for the baby is much higher than that in the bulk air of the room. So, and that's for a couple of different activities. So this is, 1 to 2 orders of magnitude difference. For humans walking, for adults walking, you're not going to see the same kind of variability because the humans walking actually do stir up the air quite a bit, adults, but you still would get higher concentrations at the breathing zone of the person than would be monitored in the bulk air in the room for resuspension. Since you're right near the source, you are the source. I wanted to talk a little bit more about the exposure disparities, and I think that this is something we really need to address. The work from the Harvard School of Public Health has, so this is the 2011 framework for setting up, okay, how do we figure out contributors to indoor exposure disparities? And so we would see disparities in the sources, the type of sources, the cooking appliances, the pesticides, other indoor sources that might be different in different communities. Also for exposure factors, the physical structure, the number of people living in the space, is it single versus multifamily, the leakage, heating systems, and then the activity patterns as well. So we would see disparate indoor environmental exposures due to these different factors. And so looking at this systemically, as we've discussed today, is really important, as well as including the communities in the work directly. So a question has already come up in the chat about are there standards for indoor air pollutants, or specifically for PM 2.5. We do have our outdoor ambient air quality standards, and they're often applied for indoor air, but I don't think that that's a good idea. And Charlie Weschler mentioned this last week in the indoor chemistry session as well, that we have the ambient PM 2.5 strongly correlated with health effects. And we know that most PM 2.5 exposure occurs indoors because we're indoors, right? But since only some of that ambient PM makes it indoors, applying these ambient mass-based standards for indoor PM doesn't make sense and would underestimate the risk. So we really need to separate the indoor generated versus the outdoor infiltrated, as shown by the work by Lance Wallace and Bee recently. Another approach we can use is that for using the disability adjusted life years. The current global burden of disease studies evaluates the ambient PM 2.5 as well as household air pollution from the use of solid fuels for cooking and ambient ozone pollution together to assess the air pollution level risk. And so using disability adjusted life years is one way to prioritize our other indoor sources as well. So I'm offering that, and there'll be more discussed next week in the session on health effects. Another framework I'd like to bring up is that is an effort being spearheaded by John Little at Virginia Tech, and this is for the modeling of semi-volatile organic compounds, so SVOCs. So bringing the community, basically providing or proposing a framework and showing where the needs are for the modeling and what we understand and what we don't understand, and working as a scientific community to build this model, to fill in the gaps, sort of agree upon a framework and work to answer the unanswered questions. And so, airborne particles is part of this, obviously, because it's semi-volatile organic compounds that would also have, partition to the particles. But we could use a similar type of framework for PM 2.5. So in summary, we know that indoor PM 2.5 is highly variable in both temporally and spatially. We have temporal and spatial variability outside, but also inside, and it's not correlated strongly with outdoor PM 2.5 typically. Also, it's very different in composition than outdoor PM 2.5. If we want to help the epidemiologists and providing good information on indoor PM, we need to separate the indoor generated versus outdoor infiltrated PM 2.5 for these studies. And then also, I haven't mentioned this yet, but it's in my summary, but the human activity pattern data, this is something that was mentioned earlier today. We have ability now with GPS-enabled devices to update our human activity pattern data. I think that most of us are still using the activity pattern data from 30 years ago. So, so definitely a large effort to do that. Also advancing the metrics and approaches for assessing and communicating indoor PM 2.5 health impacts, and increasing community engaged research to better understand the disparities in PM 2.5 and develop mitigation strategies. So thank you for your attention.
Okay.
Stop sharing.
Thank you. That was really excellent. Covered a lot of territory.